Yeah, I planned for some interruptions, so please don't save them for halfway through. Yeah, thank you all for being here. Last talk of the day. Thank you for organizing. This has been a great workshop so far. I wish I had planned ahead to come to more of it. It's been really great. So yeah, I'm going to tell you about this project that we wrapped up rather recently to sort of answer what seems like it should be an easy question, which is, if we have some application or some collection of applications or some idea for like how we might trade off between two ways of implementing an algorithm, like what's a reasonable kind of back of the envelope cost estimate for an early fault tolerant machine? And I'll define what I mean by that, but specifically the kind of like architectures we've been thinking about at Google with our qubits, where we have a big 2D lattice of qubits, maybe, at least to oversimplify. And we're thinking about things are locally connected, and we have the 2D surface code. So that's already a lot of restrictions that might not apply to every quantum computer. But for our quantum computer, how can we get a kind of good estimate of what it looks like to run something on an early fault-tolerant machine? And it turned out to be like a little bit messy. And then we wanted to be equally careful about everything. And so then it got really messy. So we did a lot of work to produce what I think is sort of a rough estimate, but hopefully it is informative to you all. I think it was an interesting process for me, and it's been helpful to have some numbers that I understand what their weaknesses are. But we'll get to that. So I did answer this question a little bit. What problem are we trying to solve? I think every talk now needs an AI-generated image, so I made one to start. This is not the problem we're trying to solve exactly, but my hope for this talk and this work more generally is that it can sort of be a useful tool to people who are thinking about algorithms and applications in this space. A thing that we've historically done in the field is do something like count the number of T-gates or the number of 2-qubit gates, and we have a nice proxy for how expensive an algorithm is. This is hopefully a proxy that is well-suited, at least to our kind of early fault-tolerant quantum computers, and you could use it as a replacement for a simpler metric when you're thinking about, how long would it take to run your algorithm, or could you run your algorithm? So it's a shovel, anyway. It's a plan for a shovel that for a computer we don't have, but in this early fault-tolerant gold rush. But really, maybe more specifically, the problem we're trying to solve, or we tried to solve, is just understanding what the transition to fault tolerance really looks like. Probably everyone here has seen this kind of picture that, at a high level, we say, oh, we're just going to keep 10xing the number of qubits we have, and maybe they'll get better, and at some point we'll be doing fault-tolerant stuff. And so, where do particular applications fall in there? And I like to think of it in terms of this picture, which I stole from some talk that existed before I joined the field. But probably a lot of you have seen this kind of cartoon as well, where we put the number of physical qubits we have on the x-axis and some notion of the error rate on the y-axis. And we sort of have this idea that over here, when our qubits are good enough and we have enough of them, we can do useful error-corrected quantum computation. But this is a sort of fuzzy boundary. And as we get closer, or we think about investing our time and energy in different kinds of projects, it's useful to think about like, how exactly do we map this out in more detail? Does my algorithm work here? Does it work here? Yes?
Yeah, this is a really old plot that was made when we thought near-term applications question mark was sort of still question mark, perhaps. One of the questions that we were asked is, did we, when this was made, I don't know what year it was made, but we still thought NISQ had some possibilities of providing utility. Do you think that question mark is still there? Should it be an X? Should it be a check?
I think it depends on what you care about. I came to the field from a chemistry background, and for me, it's a big X. So far, no utility. I'm still hopeful. Wouldn't be in quantum computing if I wasn't an optimist. But I think we know a lot of things are just very difficult in this space. I would argue that there's been some really cool physics experiments, and we've learned things from them. And we certainly learned things in developing them. So I think if you're a condensed matter physicist, you might say yes, but mostly on an analog simulator. But yeah, I'm curious about everyone else's answer too. thanks for taking my invitation to ask questions towards the beginning. So I have a few more question marks here as well. Really the point I'm trying to make is that we don't just want to do a very careful study for one application. It would be great just to have a quick and easy way of understanding, for the 50 ways I might implement something, or the 50 different lattice models I might want to simulate, or whatever. Which of them is going to work in some region of parameter space? Oh, I have a computer with this many qubits. Can I do anything? What about this many? And so that was kind of the motivating goal of this project. I want to be able to produce quantitative figures that look like this. And we'll get there. But first we need to talk about the ingredients that go into our kind of estimation. The first ingredient is that these sort of just our logical qubits. We're talking about logical qubits in the 2D surface code. We have a notion that they're laid out on a grid and they're locally connected. There's lots of nice error correction technology being developed. Most of it doesn't work in this context when everything is just on a flat grid, so we're sticking with the surface code. And we're just imagining that we have a big rectangle of these or something. People don't like to build chips that big, but it's a pretty good model anyway. And so for one of these qubits, as a function of the code distance, we know how many physical qubits we need. We have a good idea of what the logical error rate looks like. And that's what we're working with. Okay, so with these qubits, there's an observation that I found really interesting when I was actually learning about how we implement gates in this kind of architecture, which is that basically everything requires extra ancilla space and time to mediate, at least everything interesting. So I won't dwell too much on these kind of pipe diagram pictures, but I want to explain what's going on at a high level. So each of our familiar gates has an implementation down here. And the way you should understand these pictures, if you haven't seen them or you haven't seen this flavor of them, is that in the x and y directions are sort of our logical qubits. You could think of each one as a square. And then our z direction is time. And so in units of, I call them logical time steps a lot throughout the talk in the paper, but we could also say that they're roughly d surface code cycles. That's one of these time steps. What's happening here is that this way of doing the Hadamard gate it acts on this qubit, but it takes up this other logical qubit for 3 time steps. So we need the qubit we're acting on plus this ancilla for 3 time steps. A C0 gate between these two sort of catty corner qubits also requires the use of an ancilla qubit to mediate that interaction. Same with the phase gate. There's various ways of doing these things, but it's more or less true that they all have this requirement. And that managing that ancilla space and time is going to be, at least implicitly, what we're trying to do in this model. So that might worry you because we don't want to have extra space next to every single qubit. But there's a nice tool that we can use to sort of think about flexibly rearranging that space. And that's this idea of walking surface codes. And really, I'm mostly concerned with the limit where we have not that many ancilla compared to the number of qubits we're acting on. Our computer is just barely big enough to do the things we want to do. And so we're going to want to sort of move those ancilla around. And the idea behind these walking surface codes is that we can sort of drift the qubits in time at a decent speed. And importantly, whole patches of them can move together. Yes?
Maybe a kind of silly questions, but why would you have so few ancilla? You would for any useful computation, you would need to have a bunch of computational space to do what you want to do.
Well, I guess the question is, for me at least, I had in mind is, when are we going to be able to do something interesting as we build bigger and better quantum computers? And right now we're in the regime where we have not enough logical qubits to do anything interesting, by which I mean beyond classical and error corrected. At least, yeah, we can argue about that. But, so as we have more and more logical qubits, 10,000 physical qubits, 20,000, 30,000, I imagine we'll first find ourselves in this regime where we what is the smallest fault-tolerant quantum computer that can do anything useful? And then, if we can work in this regime, that would be nice. But the model I'll talk about and sort of define as we go. It might be suitable when these numbers are comparable or when the number of ancilla is a little bit larger. I think it starts to look fishier when the number of ancilla is much, much larger, and then probably want to think about things differently than we are here. Yeah. So I think it's useful. So I'm not actually going to talk about how these work at all. The only thing we care about is that we can do this. We can take a logical qubit and we can sort of glide it. Yeah?
Okay, so we might have to skip how it's done, but can we at least say how fast it is done?
Yeah, that's a great question.
Like on the order of code cycles or logical cycles? Or...
Yeah, so if you want to move, it depends. If you want to move a qubit, say 1 logical qubit's worth of distance, the techniques that we know about right now, it seems to take 2 logical time steps. And that's a little slow, but you can also move a big chunk of them all together without kind of doing it one at a time.
This seems identical to how things would move in the game of surface codes, though. Right? Like in the same time, right? But I guess the decoding problem's a bit easier. Okay, we can talk later.
I'll show you a cartoon of this, though I think will clarify how it's a little different. I think when I made that cartoon, I was more optimistic that we could do it in 1 time step. And I still sort of believe that that is true, but we'll, unclear.
That's published now.
Oh.
We have it in 1. It's
Oh, great.
1 logical time step.
Okay, great. I don't need to edit the next slides then. They're already accidentally correct. But I think that's a really important question. Like, how does this compare to the way you might think of moving things in the kind of game of surface codes way or with lattice surgery operations directly? And I'll show you that in a second. But was there a question in the back? No. Okay. So there's lots of different squares in this talk, and many of them mean slightly different things. I'm sorry. But here, what the squares mean is just they're sort of logical qubits in a big rectangle of logical qubits. And I have some of them where they're available to do this kind of stuff, whatever, mediate some gates with. And the other ones are busy storing information that I don't want to lose. And let's imagine that I want to perform a CNOT gate between here and here. There's a lot of stuff in the way. It would be rather slow to move some of these things out of the way. But with this walking surface codes technology, what we can do is we can slide everything I just highlighted in dark gray sort of collectively out of the way in 1 time step. And so in some cases, like this move from here to here, you could do that with regular lattice surgery at a similar speed. But moving these collectively in sort of as a chunk in 1 time step, rather than having to go move the first one down and then the second one and then the third one, that's quite different. And it is going to be suitable for this pretty dense packing to be able to do that. So we take a time step to do this, and then we say perform the first kind of measurement that's part of our CNOT. We take another time step here. And we look forward and we say, oh, while we're doing that, these qubits are going to be in the way of kind of completing this operation. So we're going to slide all of them out of the way. Don't take this cartoon too seriously, but it's sort of showing you the idea, like, oh, in another time step, okay, now those are out of the way, we can do this. Maybe we wanted to do something else next. And so while we're doing this, we could think about, oh, and I have another qubit here that I guess I wanted to do something with. And okay, we're going to move a bunch of stuff out of the way at the same time. And the sort of vision for the model that we're working with is that we'll constantly be shuffling qubits out of the way of each other. Yes?
So you're shuffling qubits to make gaps, so the sort of white area is still like superconducting physical qubits that you're then doing lattice surgery.
Yeah, exactly. They're available for doing lattice surgery operations or for preparing magic states or whatever else we need to do.
The idea is that if this were game of surface codes, you would have to have a bunch of white patches, sort of white area available at all times to be able to do.
I mean, at least that's one. Yeah, I mean, you can do hybrid things, but that's one nice way. Is if you just have enough space, you can do that. And then also, you can also do more complicated things than this in the game of surface codes. But the simplest formulation is that you're kind of doing one big joint measurement at a time. And here I've shown you sort of one thing happening at a time, but whoop, I guess I cut the next slide. But if we have a little more space, maybe we're also doing some gates over here, and we're preparing a T state over here, and we're measuring something over here. We're imagining that we are trying to use as much of this space as possible all of the time.
Right. If I remember from the game of surface codes, there was like slow, medium, and fast gadgets, right?
Yeah.
So in some sense, this is kind of like a slow one because you're limiting. I mean, you can't access everything all at once without doing something.
We can't access everything all at once, but it might be the case that if our operations are, say, mostly local, that maybe we're coupling these 2 qubits and these 2 qubits and these 2 qubits, we might be able to do 20 things at the same time without using that much ancilla space. And shortly, we're going to make the assumption that we're always using all of the space well at all times.
So are you assuming you're going to do Clifford gates as part of this, or?
Yeah, so I'll get there in one second, but I'll just spill the beans now. We're going to give every gate a sort of cost that is just how much ancilla space and time we think you would need to do it, accounting for a little buffer for this kind of shuffling. And we're just going to demand that we have that much.
I guess my question
available.
was going back to the game of surface code, you push all the Clifford.
Oh yeah, no, we're explicitly doing Clifford gates to enable this parallelization.
Okay.
Yeah.
Sounds good.
Yeah.
So you're eliminating these basically the idea behind this, from what I can tell, is just eliminating a lot of these bus qubits, right? Or at least no longer having this large regime of bus qubits.
Yeah.
This feels a lot like active volume to me as a psych.
Yeah. I think the thing that makes me sad when I think about active volume is that you don't have to do all of this stuff if you have long-range connections. Your life is a lot less painful.
There's still a routing problem to solve, but
Yeah.
it's easier. Yes.
So yeah, you might, here, if you have a lot of long-range stuff, you just are paying the cost of these long corridors, whether they're in separate chunks or not. So I think it's less rigorous than the active volume stuff, but it's hopefully good enough.
Yeah, counting out the cost of each gate and just adding them
Yeah,
to
yeah,
the total
exactly.
volume. That seems to be very much the spirit of how we use active volume.
Yeah.
Very cool.
I think it's slightly more justified for you all, but it's hopefully is, the aim is a back of the envelope calculation that lets us make comparisons rather than being exactly on the nose.
You don't have an explicit algorithm to solve this problem. To compile to this.
I know. Our goal was to just sort of predict if we did solve that problem, roughly what's a reasonable guess about how it might go, and I'll get into that a little more. We do some comparisons with explicit compilations just to check that it isn't totally crazy, but
Yeah, I'd imagine you get some fraction that you have to dedicate to routing and stuff like that, right? Some fraction of your qubits that have to be.
yeah, I mean, I'll get there. I'll
Yeah,
try and
I'll
remember that and answer it in just a second. I do want to say one more thing that it sort of goes into the ingredients bucket before we put it together, which is that we're also assuming this use of this magic state cultivation to do non-Clifford gates, basically. So I'm not going to review it in very good detail. Encourage you to check out this paper, or there's some wonderful talks online about it. But basically, for our purposes, it does a few things for us. We can prepare pretty high fidelity T states, and we can do it kind of anywhere we have a little bit of extra space, because it takes about the footprint of one logical qubit to do this protocol. And it's sort of spiritually like you're checking the T state in a very low distance code and then rapidly growing it using post-selection so that you outrace the accumulating errors you might otherwise worry about. And for our purposes, we're only thinking of things where we're using less than 100 million or a billion T gates. And so this is probably going to be a good enough error rate. I have some plot here that shows you sort of roughly as a function of physical error rate, which things are achievable with cultivation, at least under some way of simulating it. So, and anything that's shaded here is at least somewhat reasonable. And the more yellow you get, the more retries you're going to need. So anyway, we try and think about cost as a function of physical error rate later on. So just showing you this data briefly without explaining it very well. We can come back to it if folks have questions. Okay, but that's the third kind of ingredient we're going to use in the model because it just sort of helps justify this assumption that we can kind of use whatever space is around. Yep.
And you're only using cultivation here, no distillation on top.
Yeah.
Cool.
Yeah, and so that we're kind of focused on this regime where that's good enough.
Yeah.
Yeah.
So can you just comment on what's the idea for the cultivation?
Yeah. So I'll at least explain what this picture is referencing. So the way you should think about it is that here we're showing sort of physical qubits in like the XY plane and time going up this way. And roughly this thing fits into the space that one logical surface code qubit takes, at least for some choice of code distance. And it's a way of preparing a high fidelity T state that does some complicated stuff with a color code here and sort of post-selection. But if it's successful, which it is like some reasonable fraction of the time, you end up in a large distance code with a very high probability with a T state. And so we're just thinking like, oh, I have a qubit that's not busy. I'll try and make a T state. And we're kind of imagining that's constantly happening around wherever it might be useful. Yeah, I'm not the right person to explain in much more detail than that, but happy to point you towards them. Okay, so those are our ingredients. And I told you what they are mainly to justify the very simple thing I'm going to show on the next slide, which is sort of mainly what is going on in this cost model. So basically, we assign every operation in a circuit because this is a model that we want to work with circuits. We're thinking of someone who's coming with a circuit and wants to know like how much will it cost me to run this, even if you might not leave it as a circuit when you compile it down to error correcting operations. And so each operation, each gate gets some volume, ancilla volume. We say we need some amount of space-time volume in ancilla qubits to mediate that operation. And we're just going to sum all of those things up. And then however many ancilla qubits, I'm calling them fluid ancilla, like we have, however many extra qubits we have to mediate the computation, we're just going to say, oh, they're kind of busy all the time providing this ancilla volume. And so we'll just make the overall depth of our algorithm, it has to be larger than, it has to be large enough to provide that volume. So here the cartoon is, if you have 3 sort of data qubits and 1 fluid ancilla qubit, it might take you quite a long time. That's going up and down to do something. But if you doubled the number of fluid ancilla qubits, the blue volume, this like ancilla space-time that you need is conserved. But overall, everything is faster and cheaper because you're mediating the computations faster. Yes?
Okay, I hope to understand something a little better. So I'm thinking back to your example where you wanted to mediate some operation between 2 distant data qubits.
Yeah.
Clear a path. So in that case, it seems like those 2 data qubits used the number of ancilla qubits connecting them.
Yeah.
In this model, is it kind of accounting for that?
Yeah, so we're going to assign a cost to long-range operations that are based on the intuition that, okay, we need to spend a little time clearing a path. We need to use all the qubits in the middle to connect them. And then maybe we like close that path back up or shuffle a little bit. There's kind of a fudge factor, but the further away things are, the higher their cost will be. So that the cost for each gate is dependent on what gate it is, potentially like how far apart the qubits are if it's a multi-qubit gate. And for T gates, it's also dependent on the error rate. I have a table I'll get to in 1 second. But
And so you end up modeling that those qubits are basically fixed in place over time.
yeah, so the design goal was to like someone who likes to think about applications, but maybe like me is mostly thought about things in a NISQ context. Says I have a circuit, it's on a 2D grid. Could I run it on Google's machine that they might build in 7 years? And we could try to estimate that here. And so then implicitly you're doing what I showed you before, but we're not actually doing it. We're just thinking about it. Yeah.
So is this really as trivial as just optimize the volume as a function of like the cost of both time and space or qubit number via this equation, or is there some other trade that you're making that you have to consider with respect to the actual data qubits as well?
Well, there's a few things going on. I mean, there's a fundamental trade-off that this is like not an exact model, and if you're willing to, we've made it tractable to calculate by abandoning some level of detail. We've tried to make up for that in a couple ways that I will mention. One of them is that there's just some buffer in the numbers. And also in the paper, we provide kind of two estimates, like if you're feeling really optimistic, maybe these numbers are good. If you're feeling you want to be a little more conservative, try these numbers. It gives you an idea of the sensitivity of what you're doing to the exact numbers you choose, and it turns out in a lot of cases it doesn't matter that much. So that's one trade-off, and in reality, you won't be perfectly using all of this extra space at all times in the way we've kind of accounted for here. Our hope is that that's partially captured by like being a little conservative with the numbers we give to each gate, but then also thinking of these circuits in terms of gates that we just turn into like things that we do separately is not really optimal either. Like oftentimes you can sort of fuse different Clifford operations together, and we're neglecting that optimization, and so you could hope for some cancellation of errors. I'll show you with an example later, and there's a couple more in the paper that it ends up reasonable in some situations.
Okay, but this is highly simplified, is what you're saying?
Yeah, it's very simplified because like first criteria was it has to be easy to calculate.
Got it. Thank you.
Yeah.
So ultimately, whenever you want to build it, you're going to have an actual explicit compilation procedure to do this. And I guess, do you disagree with the following? It won't be enough to just take an algorithm and hand optimize the crap out of it, because it will be dynamically changing, because every time you use a T state, you have to randomly maybe apply another gate, and so you can't like just pre-compile this. You're gonna have to have a real-time compiler.
So
to do this. Do you disagree with that?
I think that will eventually, if we even, who knows, people might invent all kinds of crazy things in the next few years, but if we had a computer that worked like this, you probably would get the best performance by having dynamically sort of recompiling algorithms in some cases, or like having lots of options, like, oh, if this happens, so I'll do this thing. I also think we'll get a lot of mileage in practice out of a sort of like, you'll hand design something that works with a specific family of things. And I'll show you an example of that later that's, in that direction, and it is sort of resilient to, these are great questions.
Just like,
yeah?
Since you assume you can, you just directly do the paper, then you can just, if you inject T, you can just like do local correction.
Yeah, exactly. So wherever we do them, the correction, we make the T state and we do some joint parity measurement.
Right.
And then there's just Craig,
so
give me.
In that case, just like you just leave some ancilla space enough to do that, then you're fine. You don't need to recompile the whole thing.
Yeah, and you can reduce the correction to a choice of whether or not which basis you measure the qubit in, and you could push that thing away if you wanted to, and just kind of let it shuffle around while you're waiting. Okay, I do want to say that, just as an example of like what I mean by assigning a cost to each gate, these are some of the things that live on the larger table in our paper. These numbers are very subject to what kinds of assumptions you want to make. Broadly speaking, the numbers here and the ones in the main text in the paper conservatively account for like, oh, I have to move things out of the way, and now I'm gonna move them back maybe so that I didn't mess up things in the future. And it's sort of imagining things are constantly shuffling, but that you're paying this cost to like both open up and like kind of restore the configuration. And so that is why some of these numbers might be higher than you would expect for some of the folks in the audience here. Like our C0 example that we looked at, if you had all the space in the world and you weren't moving anything away, you might say that, oh, the cost is kind of just like the Manhattan distance roughly between the qubits. But if you are slowly walking qubits out of the way and you're slowly walking them back and you didn't know that Dripto put this paper out about the fast walking, or someone else did, Craig? Okay, that was my second guess. Then I don't know, maybe this number should be 3 or something now, but part of the reason this paper was annoying to write is that there's a bunch of arbitrary choices that we tried to make consistently and then justify. So you could pick different numbers here, but these are some of the numbers one might pick. In the t-states in particular, they have a cost that depends both on the physical error rate and the error rate you're willing to tolerate in your cultivated t-state. And so sometimes we optimize over that. Yeah? Yeah, so this p-phys is great question. This is, the caption didn't fit, so I just deleted it, I'm sorry. This is like if you have 2 qubits that you're acting on, or in the case of a move operation, you're moving from a qubit at some location Q1 to some location Q2. This notation is like, what's the Manhattan distance between those qubits? And for a 3-qubit gate or something, it's like the length of the connecting path, maybe. Yeah?
No, you just answered my question. Does it, like in general, it's proportional to the number of qubits you need to move, right?
Yes.
Okay.
And we're kind of assuming that implicitly that stuff is probably always in the way, and sometimes that might not be true, but there's also like wasted.
So does that read 5 times the distance? Is that what?
Yeah, so that would be like, oh, it takes you kind of 2 time steps to open up a gap, and then you like do the thing, and it takes you 2 time steps to close it. But you can also like lay it out it doesn't have to be laid out like that in time. You can kind of wiggle it backwards and forwards, and it's, yeah.
So close it means you return everything to the original, like?
Roughly, not in the sense that like you could prove that this is all correct, but if you want to be conservative, we kind of ballpark a cost that accounts for that. Yeah. Oh, yeah, that's a good question. So it's the reaction time of the system controlling the computer, which broadly speaking is like the time it's going to take it to sort of finish interpreting the measurement outcomes and like really decide, oh, this was like a 0 or a 1 that I measured. And the reason that shows up here sort of fundamentally is that the way we're thinking about implementing a T-gate, you do some measurement and then you have to resolve what the measurement outcome was before you decide on how to do the correction or not by performing a subsequent measurement. And so even if you're not in the regime where you're sort of generally limited by the reaction time of the control system, you're going to get 1 factor of that in the cost here. Yeah?
Wouldn't I expect the move in the C0 ancilla volume to also depend on just how many fluid ancilla there are to begin with? Like if you only have 1 fluid ancilla in the entire system, then you're playing that horrible game. That great
Yeah, this is going to be accurate in the regime where you have it'll be more accurate, I won't say accurate, it'll be more accurate in the regime where you have a few but not too many. And then the sort of like, if you're doing a few, you only have a few and you can only kind of do like a little chunk of this at a time. If you have enough fluid ancilla, even if it's still quite limited, then maybe the effects you're thinking about would be kind of a like second order contribution and it would still be roughly correct.
And this would be if, let's say, the fluid ancilla were 10% of the machine?
Yeah, I mean, I'll show you an example, sort of a hand compilation where if you think of it in this language, there may be like 30 or 40%, but you could tighten it up too, I think. That was just an easy thing to work out by hand.
About 5 minutes.
Okay. Well, this is a great advertisement for the paper. I'm going to, if it's okay, leave the questions and just jump to like 1 result. And maybe I'll highlight the others. I'm not going to keep people late. Okay. We also, I'm just going to say this real fast. We also separately enforce some notion of like a reaction-limited computation. I'm not even going to say what this is, really, but I don't think this is going to be that impactful in the like very constrained, space-constrained regime we're looking at, but it does help the model give sane results in certain limits. Okay, I want to at least talk about kind of one application that we looked at, and that, just because we picked a very familiar problem that people have studied the classical difficulty of it to some degree, we thought about doing this just time evolution of the Ising model, the square grid of qubits interacting with this Hamiltonian. Our task is to measure something that is diagonal, so in the computational basis, so it's easy to measure. We're going to measure it to some relatively high precision, such that at least it's like where classical methods are starting to struggle. We're going to use this FLASQ error model, or this FLASQ model, to estimate how much space-time volume our computation uses. That's going to let us estimate roughly how many errors we expect in the computation. And from that, we can say, under the simple error model that is probably good enough, we can say, here's the overhead of doing probabilistic error cancellation to remove the impact of those errors. So we're going to wrap that into the estimates I'm about to show you, which is the quantitative version of the plot that we started with for this particular problem. So for this task, which is time evolve the Ising model for 20 Trotter steps and measure something to a precision that I am saying is pretty good, if we optimize over some of the design choices, the code distance and the parameters of magic state cultivation, as a function of the number of physical qubits and the physical error rate, I can tell you in like hours, end to end, sort of how long it will take to finish the experiment we're talking about. Yes?
Did you hand compile all those?
No, so these are not hand compiled, and this is the motivation for this model is like, well, we can just vary these numbers and get a time to solution out for all of these. We hand compile this one basically, which I'll show you maybe in the last 1 minute. But this is kind of this was the original goal of the paper, is like getting to make pretty plots like this, or like this, where we say like, here's the code distance that seems the best when you optimize over things. And yeah, maybe I should end here roughly. But we think about how would we do this in a way that's legible enough to a human to sort of compile it by hand. And what we came up with, the royal we, this was my collaborator Tanuj, who's getting extremely good at these kind of hand compilation things. But basically we have all of our qubits that we're acting on in orange. We have a little red access hallway that we can shuffle around as we need with the walking surface code stuff. And then what we do to do one of these arbitrary rotations is that we couple the qubits we're acting on to one of these rotation synthesis units, a little 4x4 patch. And then we can work on it by doing effectively T-gates in the X basis or Z basis and alternating them. And then when we're done, we couple it again to the qubits we were rotating. So this is the ZZ rotation from the Ising model. And you can sort of convince yourself that you don't need to use the access hallway that often because you spend a lot of time doing the rotation and not that much time coupling them. And so, basically, you can just count up the time it takes you to, assume these rotation synthesis things are fully occupied. And really at this point, this looks quite similar to some nice work that's been done in the past, albeit, using new techniques. I'm looking at you, Michael Beverlin, because I'm not going to get to compare with your work explicitly since I'm out of time, but it's definitely inspired by that as well. But what we find is that we get actually pretty good agreement with this prediction from the FLASQ model. If we just count the number of logical time steps to do a shot in doing it by hand carefully or with FLASQ, in some sense, 76% is like a C or a C+, but it's really, it's a fine accuracy for what we're aiming for. And you could try to argue that if you were a little more clever about the hand compilation, you would like use a little bit less space or something. Yeah, I think maybe this is a good place to end. We have some other fun applications in the paper. We look at the crossover to fault tolerance. We look at other previous work. We try to argue that this approach to Hamming weight phasing approach to parallel rotations is maybe fishier than we would want. And I'm not even going to tell you the conclusions. I'll just say, yeah, thanks for your attention, and thanks for the lively discussion.